Presented by Caltech.
Welcome, everybody, and good morning. I'd like to welcome our visitors also to Caltech. Thank you all for coming for today's short course, and for those of you who will stay on for the workshop. Ronald and Maxine Linde have made this possible through their endowments of the Linde Center and the Linde Institute at Caltech. The Linde Center is really at the nexus of global environmental science research here on campus. And the Linde Institute is associated with the economics finance group here. This week, the Linde Center will focus closer to home as we try to understand something about the allocation or misallocation or over-allocation of water in the state of California. Okay, so on Wednesday afternoon, there'll be a public lecture at 4 o'clock by Gary, who's here as part of our workshop there. And it will be followed by a reception that everyone is welcome to join as well. So that's at 4 o'clock. It'll also be in this room. So our first speaker today, or teacher today, is Alex Hall. From UCLA. Alex joined the faculty in 2000. He was an undergraduate at Pomona College in history and physics. So that seems quite apropos for his talk today. And he works broadly on climate at the global scale and at the regional scale. And it is the latter that he's going to tell us about the past and future hydrology, or at least what sets the hydrology of California with respect to climate. And so, Alex, thanks so much for coming today, making your way across the basin, and look forward to your talk.
Great. All right. Well, thank you so much for having me here. This is a workshop on a very, very important topic, and I think California's water resources are extraordinarily misallocated and mismanaged, and so I think it's really time to focus the brightest minds that we have in this problem, like those of you who are here at Caltech, and I think the Linde Center is really doing a great service by focusing on this issue. My task today is to describe the physical system and the way that it constrains water resources. So there's the natural environment, of course, is what we have to start with when we think about how water is distributed and allocated. And so that's what I'm going to be talking to you about today. And I have divided the talk into four different parts. The first half of the talk, the first two parts, is focused on the current climate, the state of affairs as it is now, or has been in the past few decades. So we'll be giving some context about what shapes the climate in this region, and then I'll talk about how precipitation is distributed in the current climate in California. And then the second half of the talk, I'm going to pivot and an acknowledgement of the fact that the climate that we have is not stationary, which is to say that it is changing for reasons that we're all familiar with, the increase in greenhouse gases in the atmosphere. And so we have to think about how climate change might also impact hydroclimate in California and water resources. So I'll be talking about the intensification of the hydrologic cycle at the global scale, and then changes in hydrologic extremes, which I think are particularly important for California. So let's dive right in with the first part, which is some global context for what creates the climate in this region. So we have a Mediterranean climate, as I'm sure many of you know, and just some background on how precipitation is distributed globally. This is just stepping through the months of the year. This is showing the global distribution of precipitation on average over the entire planet. So the dark blue colors are showing where there's a lot of rainfall, and the white colors are showing where there's very little. So what creates this distribution of precipitation? Well, The rising and sinking of air is what drives the distribution of precipitation across the globe. And there is a key overturning cell, a rising and sinking of air cell, if you will, which is known as the Hadley cell. And this operates in the tropics and in the subtropics, so between, say, 35 north and south. And near the equator, air is heated by solar radiation. So this heated air contains water vapor that is evaporated from the land or the ocean surface. And then this water then rises in the atmosphere. And as this air rises, it cools off. And cooled air can hold less water vapor. And so the excess begins to fall out as precipitation. And the result is that we have this rain belt in the tropics where we have very heavy precipitation. And that's associated with the rising branch of this Hadley cell circulation. So after this air rises, it then moves poleward to the subtropics, right around 30 degrees north and south. And then it sinks and it warms. And this air is now very dry since nearly all the water has precipitated out in the rising branch of the Hadley cell in the deep tropics. And so the result is that we have the world's major deserts in the subtropics. And so you can see here that typically flanking the rising branch of the Hadley cell in the deep tropics, we have these areas of extreme dryness in the form of the world's great deserts. And California is located at the northern edge of a great subtropical dry zone. So if you look here, you can see that if we just look south of here, there's an area where there's really very consistent dryness. And we're just at the northern edge of that. And this North American, North Pacific zone of sinking and dryness has its greatest geographical extent in northern hemisphere summertime. And so we tend to have very dry conditions in the summertime in California for that reason. Okay, now I've taken this map and blown it up and just to focus on the northern hemisphere here. So this is the same thing you've been seeing before. And I want to talk about a secondary precipitation maximum, which is distinct from the one in the deep tropics, and that's in the mid-latitudes of both hemispheres. And you can see it especially pronounced in the wintertime. So as we go into November and December, you can see there's a secondary maximum of precipitation that develops in mid-latitudes. And this is the so-called mid-latitude jet stream or storm tracks. And it varies seasonally. It's greatest in the winter. And you can see the seasonal variation very clearly in the northern hemisphere. And these, in the North Pacific and North Atlantic, there are these storm tracks, these zones of extreme storminess that develop in the North Pacific and North Atlantic. And these are associated with a very strong eastward mid-latitude jet stream in both hemispheres at right around 45 to 55 degrees. That's where the center of action is. And this jet stream is highly turbulent, and within it there's turbulence, rising motion, cloud, and precipitation. And in the wintertime, California is located at the southern fringe of this northern hemisphere mid-latitude jet stream. And this is why the state receives some precipitation in the wintertime, which actually saves it from being a true desert, as you would expect if it were located directly in the subtropical sinking zone. And this is why California has this Mediterranean climate. So Mediterranean climates are, like California, they occur on the western edges of continents between roughly 30 degrees and 45 degrees in latitude. And they are they're very interesting, ambiguous hybrids of deserts, which are found in the subtropics, and much wetter mid-latitude climates, which are found in the mid-latitudes. And these Mediterranean climates are characterized by very long, dry, and very hot summers, and short, wet, and mild to cool winters. And so this is the global context then for the climate here in California. And so California has a lot in common with these other regions in terms of its water resources. And this is actually perhaps has policy implications because some of these areas have found very interesting solutions to their own water problems. For example, Australia is an example that I think probably in general a little bit ahead of California in terms of their coping with water scarcity. All right, so we have this Mediterranean climate, and so what is it, how is precipitation then distributed within California, both in space and time, as a result of this Mediterranean climate? So that brings us to part 2 of the talk. Most of the precipitation in California occurs in the form of so-called orographic precipitation, meaning that it occurs when moist air masses that are embedded within this mid-latitude jet stream that brings rainfall to California, when these are forced upward over mountains. So just as rising air in the tropics is forced to cool and precipitation is then the result, if you force air to rise up over mountains, it also produces precipitation. And this mechanism is very evident in the distribution of mean precipitation over the state of California. So the most precipitation occurs at the highest elevations. So here's the mean distribution of precipitation. And you can see very clearly the major mountain complexes in the state of California. Even in Southern California, you see the transverse and peninsular ranges. You see the coast ranges here. There's the Sierra Nevada, which is really getting most of the precipitation in the state. And then you get up into the coast ranges up in the northern part of the state. So it's very clear that the mountains are the main beneficiaries of the mid-latitude storms that arrive in the wintertime in California. Another thing that's very clear is that more precipitation falls in the north than in the south. Northern California is a little bit more like the mid-latitude climate regions that I mentioned earlier, since mid-latitude disturbances visit this area much more regularly. So across the state from north to south, we have a transition from a more mid-latitude-like climate to a more desert-like climate in the south. By contrast, Southern California, where we are, is, although it's still, especially in this part of Southern California, if you're on the coastal side of these big ranges, it's definitely a Mediterranean climate, but it's a little bit drier and a little bit more like the desert regions. And that's because these mid-latitude disturbances visit less frequently. And this is the origin of, I can't remember who said it, but there was some famous water resource engineer said that we have to move water from north to south because the people are living in the south and the water's all in the north. And a lot of California's water resource infrastructure is set up to bring this precipitation southward. Now, another point that's important is that at higher elevations, the temperatures are generally cold enough that precipitation falls as snow during the wet winter season. And mountain snowpack is therefore a key water resource, providing about 60% of California's fresh water. So this zone, the spine of the Sierras, is giving us about more than half of our water is coming from mountain snowpack. Snowpack acts as a natural reservoir, storing water in frozen form until it gradually melts and runs off in the spring and summer. And again, the water resource infrastructure is shaped around this natural reservoir. And all of the man-made reservoirs that are at the base of the Sierras are sized, assuming that this snowpack exists. And as we will see, this is a problem because snowpack is disappearing. Now, another feature of California's hydroclimate is that it is also unusually variable in time. And this is kind of a little bit of a statistical, nerdy figure, but it's worth understanding. This shows the so-called coefficient of variation for annual total precipitation across the United States. Okay, so here's the entire US, and at every single weather station, this number has been calculated. Okay, so what is this number? This is the ratio of the standard deviation of precipitation, the variability in precipitation, to the mean. So if this number is very low, it means that the variability is small compared to the mean value. Okay? So if you look in the eastern part of the US, this number is about 0.1. think about what that means for water resources. There's an incredible consistency from year to year in how much rainfall comes in the eastern part of the United States. Take a look at California, and especially Southern California. This number is incredibly high. This coefficient of variation is something like 0.5, 0.6, 0.7, meaning that the variations from year to year in precipitation are as large as the average amount of precipitation. So some years there's very little rainfall or snow or precipitation, and some years there's really a lot. And this extreme variability is a big challenge associated with water resources in the state of California. Okay, so where does this variability come from? Mainly, it comes from this phenomenon known as atmospheric rivers. These are narrow bands of atmospheric moisture that cause very heavy precipitation when they make landfall, and especially as they pass over mountains and are affected by this orographic precipitation mechanism that I mentioned a moment ago. These are commonly known as the Pineapple Express, and they almost always coincide with heavy precipitation, and they're responsible for somewhere between 20 to 50% of California's precipitation and stream flow. So we get these plumes of moisture from the tropics that hit the coast and produce a lot of rainfall. And most of our precipitation accumulates on just 5 to 15 days of the year when atmospheric rivers hit the coast. And the difference between a very, very wet year and a very dry year is maybe 2 or 3 of these atmospheric river events. And so you can see why the hydroclimate is so variable, because it's really just a few rolls of the dice determine whether we have a rainy year or whether we get a lot of rainfall or not. And so this is the fundamental mechanism for that. So each atmospheric river event makes a very important contribution to the state's total precipitation, and just a few atmospheric river events can make the difference between a very wet year and a dry year. All right, so just to illustrate this again, this point really can't be emphasized enough. Here is the precipitation averaged over the Los Angeles region for 1981 to 2000, so it's a kind of a climatology of the past few decades, if you will. And it's broken down by 4 months of the wet season, December, January, February, and March. And I plotted 5 different data products. There are many different ways to measure precipitation. And it doesn't really matter. Here's the list of them. It doesn't really matter what they are. They all tell the same story, which is that there's a lot of variability from year to year. Each one of these dots is one of those 20 years of precipitation values. And so if you look, for example, at January, you see this bouncing around a lot. And in particular, there are a few years where there's really a lot of precipitation coming in. And then there are also some years where there's almost nothing. So I'm sure you've all experienced this. Some winters, it's almost like it's summer. There's no rainfall. And then other winters, it'll rain for, say, the entire month of February. So really dramatic differences between wet years and dry years. And this is a huge challenge if we're talking about local capture of water, because the water resource infrastructure has to be designed for flooding as well as water storage. And so in Southern California, the solution has been to just channelize the rivers and let the water flow to the ocean, because it cannot be managed. It comes in such large quantities over such short intervals of time. And so we won't try to infiltrate it and store it. We'll just simply let it run off. This probably is something that, well, this certainly needs to change, but it's not an easy engineering challenge. All right, and these very wet months correspond, again, to this frequent occurrence of atmospheric rivers. All right, so hopefully this sets the stage for California climate in the global context, and also the spatial and temporal variability in precipitation in California. Let us now move onwards and address this issue of non-stationarity in climate. In other words, the fact that we live in a changing climate. All right, so I'm sure you've heard this term before, hydrologic cycle intensification. It refers to the global increase in precipitation associated with the increase in greenhouse gases in the atmosphere. And so to talk about the hydrologic cycle intensification, we have to take a step back and say a few words about the way that the global climate community has derived this information about climate change and hydrologic cycle intensification in particular. So the climate community has undertaken a set of coordinated climate change experiments. And there, as many of you may know, there are about 36 or so global climate modeling centers around the world, each of which has developed a so-called global climate model. This is a computer simulation of the climate. And typical resolutions of these models are 100 to 200 kilometers. And to prepare for the 2013 IPCC report, this was the big United Nations report that is meant to encapsulate the consensus surrounding climate change. These modeling centers around the world organized a common set of climate change experiments to be undertaken at every single modeling center. And this is a kind of amazing self-organization of the scientific community to standardize climate change experiments. And it gets this very jargony UN name, the Coupled Model Intercomparison Project Phase 5. It's also known as CMIP-5, and so you'll hear me refer to these simulations as the CMIP-5 models or the CMIP-5 simulations. All right, so these CMIP-5 organizers created 4 standardized radiative forcing scenarios to be imposed on these global climate models. And so here is time going from 1850 to 2300. And this is the radiative forcing, the change in energy balance associated with increases in, for example, greenhouse gases in the atmosphere. And this black curve is just simply the observed changes in radiative forcing over the past 150 years or so. And then we have 4 different future scenarios that are forked off right around 2005 when these experiments actually begin. And the most aggressive forcing scenario is known as RCP 8.5. It's the one where greenhouse gas emissions continue to increase as they have been increasing over the past decade or so. And this scenario has the nickname business as usual because it implies a continued increase in greenhouse gas emissions. And this is the path that we have been on since these forcing scenarios were created. And we also might imagine a mitigation. So anyway, on the plot here, this red curve is RCP 8.5, and you can see it's a steady increase in heating of the planet going forward over the course of the 21st century. And then there's a mitigation scenario, which is similar to what is envisioned by the 2015 Paris Climate Agreement, and this one is RCP 4.5, and you can see it's got a light blue color there, and it has a much smaller increase in atmospheric or planetary heating. All right, so these are the standardized set of scenarios that were imposed on the global climate models. So what happens then to the hydrologic cycle, which is the topic of today's discussion? So this plot shows the global climate model projected precipitation changes by the end of the 21st century compared to the end of the 20th century. So if it's blue here, there's an increase in precipitation, and if there's a decrease, it's these yellow to brown colors. And these are the values that are averaged across the global climate models. So this gives you a sense of the most common response of the models. And this is associated, again, with the RCP 8.5 business as usual forcing scenario. The other forcing scenarios have very similar spatial patterns, and the individual GCMs tend to have similar patterns as well, although they can be dialed up or dialed down compared to this one, consistent with more or less warming, depending on the scenario and the model. All right, so clearly, the projected changes in precipitation are not uniform at all across the globe. There are significant increases in the deep tropics, but there's very little precipitation or even maybe a decrease seen in the subtropics, in the areas that are already quite dry. And in the mid-latitude rain belts, a significant precipitation increase is also seen. So looking at these changes together, we can see that with climate change, areas that are currently wet, the deep tropics get wetter, and the mid-latitude rain belts also are associated with more precipitation. And the areas that are currently dry get drier. And this is why the term hydrologic cycle intensification has been associated with these particular changes, because they're an exaggeration of the existing distribution of precipitation. Now, as we've seen, the Mediterranean climates are these ambiguous hybrids of the subtropical type climate, the desert climate, and the mid-latitude climate. And they're at the boundary between these dry and wet zones. And as a result, the GCMs tend to predict only very weak changes in precipitation in these areas. So if you look, for example, at California, it's kind of not really clear what would happen to precipitation in this part of the world. So at UCLA, we've recently completed some high-resolution regional climate modeling over the LA region. And one of the questions we looked at was changes in the water cycle. We developed a so-called hybrid method to downscale GCM information to very high resolution using so-called dynamical downscaling. This is similar to a global climate model, but performed over a limited area at very high resolution. And then a simple statistical model that mimics this dynamical model. And because it uses both so-called dynamical and statistical techniques, we call it hybrid downscaling, but that's not too critical for this talk. The most important thing is that we were able to downscale all of the GCMs associated with the CMIP5 archive. And we looked at several aspects of climate. Here we're going to focus again on precipitation. So I showed you this picture before. This is the precipitation averaged over the LA region, broken down by 4 months of the wet season, according to 5 different data products. They all tell a very similar story of very large interannual variability in the LA region. One of these data products, the black dots, is actually our regionalization of climate, our simulated climate over the period 1981 to 2000 using this dynamical downscaling technique that I mentioned. And these others are closer to true observations. In any case, we also projected future changes in precipitation in this region. This is under the RCP 8.5 forcing scenario for a mid-century time slice. And so the big red dot here is the ensemble mean change. And these little dots represent the changes associated with every one of the GCMs that were downscaled. And one thing that is very clear here is that, first of all, the ensemble mean projection is 0 precipitation change, so no change at all in average precipitation. And also, this interannual variability is just huge compared to the spread across the GCMs. So even if you believe that the GCM that is associated with the most precipitation change is the right one, the interannual variability in this region is very, very large compared to that signal. And so the upshot of this is that we really don't expect a significant change in average precipitation coming into Southern California associated with the changing climate. And again, this is because we are at this boundary between these areas that get drier and these areas that get wetter. So here's where our Mediterranean climate kind of saves us, right? Because we are kind of ambiguous on whether we're mid-latitude or whether we're desert, we don't really expect a big change in mean precipitation. All right, changes in extremes are a somewhat different story. So let's end by focusing on that. So the 2003 IPCC report that I mentioned earlier provides information about changes in precipitation extremes at the global scale. And the report quantified the ensemble mean or average change in precipitation accumulation over any 5-day period within a given year. So basically it's looking at the 5 days of the year that have the most rainfall. It's kind of an arbitrary way to measure it, but it's basically looking at extreme precipitation in these global climate models. So here is how that change is distributed over land areas under the RCP 8.5 greenhouse gas forcing scenario. So these blue numbers are indicating an increase in the amount of rainfall that falls on those 5 wettest days. And you can see there's a lot of blue on here. And these increases are generally about 20%. And what this means is that the rainiest consecutive few days will be about 20% wetter on average over the globe. This change is one of the most robust features of these projections. The most robust feature is warming. They all get warmer. But there's also this change in extremes, which is much more robust even than the change in the hydrologic cycle on average. It's this change in extremes, which is very, very, very common across all the models, and it's also found at nearly every point on the planet's surface. And here we're just showing the land areas, since those are the important areas for humans, but this really occurs everywhere. So a very robust change. Why does this happen? Well, as we've seen, precipitation generally occurs when air masses containing large amounts of water vapor are forced by atmospheric flow to converge and then rise. And this process produces condensation, clouds, and precipitation. And the increase in heavy precipitation events is driven by a general increase in atmospheric water vapor as climate warms. That's one of the consequences of warmer temperatures, is that the atmosphere can hold more water vapor without saturating. And so there is more water vapor in the atmosphere, so when there is convergence of air and rising motion, there is more precipitation. And so this is, again, a very robust feature. So if water vapor generally increases in a warmer climate, then these converging air masses will hold more water vapor and will produce more precipitation. And in spite of these results and the robustness of the general physical arguments that underpin them, it is still difficult to be quantitative about changes in precipitation extremes at the regional scale. And the one reason for this is the coarseness and the biases in the global climate models at the regional scale. Still, I think we can say a few things. We can begin to regionalize this information by first focusing only on the GCM data over California. And so in this plot here, every column is a 20-year period of the 21st century. So here's 2001 to 2020, and here's 2081 to 2100 with these 5 20-year periods distributed over this plot. And then every single one of these rows here is one of the global climate models. And the colors represent the number of extremely wet years in the areas of the GCMs associated with California. And an extremely wet year is defined so that one extremely wet year is expected every 20 years. Okay? And this is based on the historical period, 1900 to 2005. All right, so if one of these boxes is white, that means that that particular GCM is projecting numbers of extremely wet years that roughly match those in a historical period of basically the 20th century. And the bluer these boxes are, the more the numbers of extremely wet years exceed the expectation that's set by the historical period. So in many GCMs, by the end of the century, there are 3 to 5 extremely wet years per 20-year period instead of just 1. So you can see this is getting increasingly blue in many of these models. Now, this report also provides information about the length of time between precipitation, so-called dry spells, This is a very rough measure of the increase in drought that is driven by a precipitation deficit. We can have drought for a lot of reasons, but one of them is a lack of precipitation. And here is how this changes. The brown to red colors are showing increases in the length of dry spells, and the blue colors are showing decreases. Many of these areas show an increase in consecutive dry days, especially the areas that are already a bit dry. And for California, we can play the same game for the extremely dry years as we did for precipitation. And these also tend to increase. We tend to get a little bit redder as we go towards the right, and we get towards the end of the century. But the numbers generally don't exceed natural variability levels until the end of the 21st century. So the changes in extreme precipitation seem to be a bit more robust than the changes in extremely dry years. Now, a big caveat on this is that water availability during a drought or during a period of precipitation deficit is driven by more factors than just a deficit of precipitation. Warming also plays a significant role in reducing snowpack and enhancing evaporation. And this is something that we have to confront, certainly in California. So we're also completing at UCLA a high-resolution regional climate modeling project over the Sierra Nevada, this area that supplies about 60% of California's water resources. And we're using the same methodology as in the LA region to downscale all of the CMIP5 GCMs to roughly 3-kilometer resolution. And as in the LA study, we looked at several aspects of climate. Here, I want to focus on some key hydrologic variables, snow and soil moisture. So there's a loss of snow, as you might expect, with a rapidly warming climate. So here is the total snow water equivalent volume for 2091 to 2100, the end of the 21st century, for this RCP 8.5 forcing scenario. And this is given as a function of elevation in the Sierra Nevada. And so here's what happens by the end of the 21st century under RCP 8.5. This is the current value of snowpack. And so you can see that the volume of snow declines very dramatically, especially between 1,500 and roughly 2,500 meters. These mid-elevation areas experience very big declines in snowpack. This is given in terms of total water equivalent volume. This is a measure of the total water resource that's stored in the snowpack. And if you add this up over the entire snowpack, the losses are about 50%. So about half the snow is lost under business as usual. Yes, question in the back.
Good morning. Fantastic presentation thus far. Is that mainly a temperature effect? Is it just melting, or there's actually less rain?
It is almost exclusively a temperature effect. There's less precipitation coming in as snow and more as rain, and more of what does fall as snow melts sooner.
You're still going to get the rainfall.
Correct. Correct. And so this is essentially a water storage challenge, right? Because as I mentioned earlier, the reservoirs are sized assuming that this natural reservoir exists. And the reservoirs have a function not only for storage, but also flood control. So if the precipitation is coming in as rain, that means that the reservoirs have a water management problem because they don't have that steady runoff of snowmelt in the summertime. Okay, so this is the RCP 4.5 mitigation scenario. This is probably the most optimistic scenario we can imagine. This is assuming that all the nations of the world follow through on their commitments in Paris last year. And in this case, too, there's a pretty significant decline you can see in snowpack. All right, so I mentioned these reasons for the loss of snow, more rain and less snow, and more melting of snow. And there's also a process known as snow albedo feedback, which accelerates snow loss. As snow retreats, it uncovers land that absorbs more solar radiation than the snow would have. That leads to more warming in these mid-elevation areas where the margins of the snow are located. and that leads to a further loss of snow. And this process is actually quite important in the Sierra Nevada. All right, so that's the snowpack. There's also changes in surface resources. So this is the ensemble mean change in soil moisture by the end of the century compared to the last decade of the 20th century. Again, for this RCP 8.5 forcing scenario. So this is the Sierra Nevada. It's kind of hard to make out. Here's the state of Nevada, elbowing its way into California, and here's the coast of California, and here's the Sierra Nevada. And this is the percent change in soil moisture. And this percent in the upper right corner is the moisture loss that's averaged over this entire domain. And these values are averaged over the summertime dry season. So when there's not a lot of precipitation coming into this region, there's a lot of evaporation happening because temperatures are warm. And these changes do factor in any potential precipitation increases that occur in some GCMs during the wet season. So a very pronounced drying of soils in the mountain areas. In other words, increased evaporation and snow loss due to warming outpace any increases in incoming moisture, leading potentially to a significant overall drying. And even if we look in the mitigation scenario, the RCP 4.5, we see pretty significant loss of water. So this points to the likelihood of more severe future droughts and fire seasons. This also is potentially a loss of water resources because we capture water not through capturing precipitation, but through capturing stream flow. And if there's more evaporation and the soils are drier, that is going to lead to less stream flow that we can actually capture, even if precipitation remains unchanged. And so this is not only a significant ecological challenge, ecological management challenge, fire management challenge, it's also a water resource issue. And I would point out that the drought that we've experienced over the past few years is very similar to the type of conditions that we expect in the future. If there is a precipitation deficit, that results in enhanced dryness because of warmer temperatures and enhanced loss of snow because of warmer temperatures as well, which makes the water resource challenge even greater. All right, so let's wrap it up and summarize. So California has a Mediterranean climate with highly variable precipitation. Most of the precipitation occurs at high elevations and in the northern part of the state, and mountain snowpack is a very important natural reservoir. In our future climate projections, the mean precipitation doesn't change too much, but very wet years are expected to occur more frequently, and very dry years are expected to occur somewhat more frequently as well. So a little bit of an increase in extremes, and loss of snow and enhanced evaporation due to warming are expected to exacerbate drought conditions in low precipitation years. So this was my attempt to, I think, just summarize at a very high level the state of knowledge about California climate and climate change, and even a little bit under time, I think. So hopefully save the workshop a minute or two. All right, so thank you very much.